I am going to, when this starts, I'm going to continue with the lecture that we had on Monday. For Tuesday, or for Wednesday, today's Tuesday, make sure that you have completed all of, was it chapter 26, is that the one we're in right now? Yes. Make sure you've completed concept codes for all of chapter 26 for Wednesday. Before I talk about astigmatisms, I have handed back all of the tests this time, except for one person. I haven't graded yet, it's my fault. And the scores on this were odd. It's a very bimodal distribution. So just so people can see what it looks like, we have 1, 2, 3, 4, 5 people there. There's the way it broke down. There are 5, I graded out of 90. There are 5 A's and 5 F's. Now, I think you all understand, I don't want people to get F's. I want people to understand the material and to be successful in this class. Otherwise, it's wasting all of our time. So I'm not happy about that. If you have things you don't understand or you think I missed something in the grading, please come talk to me. I want to try to make sure that we have as fair and as good and representative the grades as we can. So I just turned in the midterm grades. There's nobody with an F on a midterm grade, in case you're curious. But I want to make sure everybody sees that and understands how the grades went. And of course, you know that the solution is on Moodle, so you can view the solution that I made to see what may have gone wrong there. Any questions on the test? I mean, not like how do we do problem number 3, but about process or grading or anything. Okay, then on with the vision. We talked about 2 vision problems last class period. What were the names of the 2 vision problems? Myopia, hyperopia. Myopia, what's the common name for myopia? Nearsightedness. What's the common name for hyperopia? Farsightedness. Now there is another related difficulty to those 2, and it's not the astigmatism you see up there. The third related one is presbyopia. Anyone have any idea what presby means? Like Presbyterian presby? It means old. So presbyopia is old people vision. Now, you all have parents probably, and I still remember quite distinctly when I was in grade school, Mom would read the morning watch to us every morning at breakfast, and like my 8th grade year, she was reading like this in September. By the time we got to December, she was reading out here. By the time we got to June, she was holding the book as far away from her as she could. And I was like, why, Mom? Why? Well, I just can't focus anything closer. That's presbyopia. It comes on when you get older. Fortunately, it hasn't hit me yet. Doesn't mean it won't. So presbyopia is a problem with the, which point, near point or far point, which one am I having a problem with if I have to move things farther and farther away to read it? The near point. It's a problem with the near point moving out. But it's not caused by the, well, what was the other problem we have with the near point that we learned about yesterday? The one where we couldn't see things close. What do we call it if you can't see things close? You're farsighted, so it's hyperopia. So it's similar to hyperopia, except a lot of people get the 2 confused because they're both problems with the near point. But hyperopia, we could say it was either caused because the eyeball was too short or the lens was too weak, as the eyeball is too flat. Presbyopia is a problem with the lens instead of the cornea. Right? The 2 that we talked about, the hyperopia and myopia were problems with the cornea or the length of the eyeball. But presbyopia is with the lens. What does the lens of the eye do? Accommodation allows you to vary the focus. You can focus on different lengths. And so that presbyopia, the lens gets hard. And as it hardens, it doesn't deform as much. And so you can't accommodate as well. And so what happens is your far vision is unchanged, but your near vision, the accommodation starts moving out. So you can take a situation like we had Diksha, who came up and had us test her vision. And her range of vision was something like this, which would clearly be nearsighted. If Diksha gets old and starts to suffer from presbyopia, which one of these two is going to change? The closer one. What's it going to do? Go out. And so go like this, so she might get to where she can only see in this 1-inch range. That would stink, right? So right now, with Diksha's vision, she wears the eyeglasses, and it moves both of these things out. So this one goes to about 25 centimeters, and that one moves to infinity. And she sees just fine. But if she were to get the presbyopia, when she moves it out, they would both move out there. And so with her eyeglasses, you know, hey, look, I can read from 3 meters away to 10 meters away or something, but I still can't read a book. Well, Ben Franklin came up with a solution to this. What's Ben Franklin famous for in optics? Bifocals. The idea of the bifocals, you have two lenses, one for reading things, one for close things, and one for far things. So that you can have a narrow range because you suffer from both myopia and presbyopia and still be able to see near and far things. So that's the point of bifocals. And these days we have gradient lenses where you just adjust your head and you have a different focal length. So you can have a really narrow range that you can focus. You go like this and you can see far away. You go like this, closer, 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 closer. That's how those things work. So when you first get them, it's kind of hard for people to adjust. Okay, first Diksha, then Cassie.
So how does LASIK fix the vision?
Okay, how does LASIK surgery? Now there's a section in the textbook on LASIK surgery. At least there are a whole lot of questions I could have chosen about LASIK surgery. Let's go to what they did when I was in college age. They had photorefractive surgeries possible when I was in college. What they're doing is they are modifying the cornea to make it so it has a different curvature, thus a different power, and adjusting the focus. So let us say that you are myopic. If you were myopic, there were two ways we could describe myopia. Myopia was caused by what were the two different ways of describing it?
The eyeball is too long or the cornea was too strong.
Okay. Eyeball too long or cornea too powerful. I'm using powerful because the power is 1 over the focal length. So it has too short of a focal length. So if I want to fix this, I am not going to do a surgery on the cornea that affects the length of the eyeball. Hence, I'm just going to affect the cornea, change that shape. So if I'm going to fix myopia, I missed a letter. I knew I had the letter on the other side of the P. If I'm going to fix myopia, what am I going to have to do to the shape of the cornea to make it have a longer focal length? Make it what?
Less curved.
Make it less curved. I'm going to need to flatten it. Now, how do you flatten the cornea? Back in the old day, they cut a flap, they cut a circular flap. They have a little machine that does it. They can either completely separate it or just flip it back so it's just hanging out. And then back in the day, they would say, okay, well, to flatten it, let me put a bunch of incisions here. I'm going to make an incision here and here and here and here and here. And they calculate how many incisions they need to make so that it will scar over. And as it scars, it'll get thicker where they made the incisions. And so by the cornea scarring, it gets thicker there and they flatten it. And that's really what they did to people. I had a girlfriend of a classmate when I was in graduate school who had that surgery done. And I was thinking, that seems barbaric. What if I scar more or less than they expect? Well, you had a plus or minus. They didn't expect to get you any better than 20/40. 20/40 means at a distance of 20 feet, you see with the visual acuity that a normal person sees at a distance of 40 feet. And they said that's the closest we can get because your scarring may be different than we anticipated. Then they put the flap back down and you're good to go. Now with the photorefractive surgery, Tori asked me what I did my PhD work on. I did my PhD research on vaporizing transparent materials with lasers. That's what they do with the current LASIK surgery. They measure what your lens shape is and what it should be, and then they just have a computer program that says, okay, we're going to need to vaporize this much lens here and this much lens, or cornea, not lens, this much cornea here. They still have to cut that flap, flip it back. They use the laser, a pulse laser with just a little grid, and they move it around your eyeball and flash it so many times to vaporize so much material. And then they put that flap back on and you're good to go. Now, doing this way with the laser, they have a much better control. And so they can get you better vision. So it's definitely a better procedure. But that's what they're doing. Now, for fixing myopia, you have to then thin the center of the cornea. Well, that's not a problem. For fixing hyperopia, what do you need to do? You can't make it fatter in the center, because you're not making scar tissue here, you're just taking away material. So you need to make it thicker at the edges, or thinner at the edges. But if you make it thinner at the edges, you run the risk of getting too thin and having to tear the cornea. So fixing hyperopia is a more difficult procedure, and there's more limitations because you can't go that thin. Whereas for fixing myopia, it's no big deal. You're clearly going to still have a convex nature lens, so you're not going to make it so thin that it's ripping. Now this cornea, it's obviously very important to your vision. My grandfather, he played some semi-pro hockey, played some semi-pro baseball. He played catcher and goalie, and in both, he took objects to the eye, damaging his cornea so he couldn't see out of one eye. And later on in his life, physicians say, we can fix that, but by that point, the eye that was blind was just doing this, and there's no point in fixing it. What do you do these days? Well, what's another corneal problem? What? Cataracts. Cataracts is another corneal problem. In cataracts, it's not so much the shape of the cornea that's the problem. It's that the cornea has regions that are no longer transparent. Well, that's kind of a problem for vision. And so you can have things like corneal transplants where they take somebody who's died, they take the corneas out and put them in you. I'm guessing they do some shaping of them. I don't know this. And so you can have that. I think they have synthetic corneas. I've seen recently using stem cells to try to grow new corneas. A really, really sad story that I always have to tell. My parents were missionaries in the Philippines a couple decades ago. And there was a guy who had grown up just dirt poor. He worked really hard colporting to get some money together so he could have a corneal transplant, because growing up dirt poor, he had malnutrition that contributed to him developing cataracts. So he got his money straight together, went to the hospital, had a corneal transplant. A week later, they're at church. He's actually teaching Sabbath school. When health officials come to the church and say, "Where is he? We need you to come with us." And everybody's all, "What?" He died like 3 days later because they'd given the cornea from somebody who died from, from rabies. The person had died from rabies and somehow hadn't been known that they died from rabies. They transplanted both corneas, one to him and one to somebody else. The other person had already shown signs. He hadn't shown signs yet when they came, but it was too gone. It tears my heart out because, I work so hard to make your life better. So I just have to tell that because it's talking about these issues. So thank you for asking that question, Diksha. Gave me a nice segue into talking about how we do the corrections. Now, something else I like to point out, this one actually is really funny to me. When I was my first year of teaching, I was talking about vision problems, and we talked about how we can correct these with lenses. Well, the first eyeglasses were actually created by Chinese people. I had a Chinese student who was like, yeah! And then I talked about, what do you do when something's a little fuzzy and you're trying to focus on it? You squint. And then the student got really angry at me. But her anger was misled. It had nothing to do with eyes of Chinese people. But the first eyeglasses were invented by Chinese people, and what they did was they made bamboo slats, so it was kind of like you were squinting. And we will learn soon about diffraction and why that helps. Right now, I've already said that I can see better during light time than in dark because of the size of the pupil. And that's what those first glasses were taking advantage of. Now we have much more sophisticated glasses. Now on to the topic of this slide, astigmatism. Now I'm not sure that I would use the quality, well, if I go like this, that this at least gives us better quality. I'm not sure that I would use this up here. I would use the book or something like that more to judge astigmatism. But astigmatism is determined by looking at something like this. Everybody's had an astigmatism test, right? You go to the eye doctor. No?
No, probably. They just don't know. Is that the house?
I haven't been to that doctor in 10 years. So. This is the traditional way. You look at this and they just ask you, which lines look the darkest to you? Do lines look all the same or do some look darker? Darker. Some look darker. I can tell that I have an astigmatism because I see the horizontal lines as darker. And I rotate my head just to make sure, and it stays the ones that go that direction with my head.
So if they're all the same?
If they're all the same, then you don't have astigmatism or it's corrected by your glasses.
Oh, I can't see.
Okay, so what's going on with an astigmatism? Why is it so simple to determine this? Astigmatisms are the result of an eyeball that is not symmetric. If your eyeball is not symmetric, you can treat it like you have two different lenses, one that's focusing light on one axis and one that's focusing light on the other. So since I see the horizontal lines as darker, that means that my eyeball is focusing the light horizontally better and not focusing as well vertically, so the light's getting spread out more and it looks fainter in the other direction. I think I said that right. So I have vertical, horizontal for my orientation for my slight astigmatism. And of course your eyes can be different. So that's what astigmatism, it's an asymmetry in the eyeball. How do you correct that asymmetry? Well, you use a lens that has an asymmetry that if the eyeball is stronger in the vertical axis and weaker in the horizontal, your lens is going to be stronger in the horizontal and weaker in the vertical, so that in the end, you have the same strength in both axes. So that's how astigmatisms are fixed. You guys are all so young. You probably don't know that contacts can't correct astigmatisms, because now they can. But back when I was in college, people could get, high school even, people could get contact lenses. Imagine the technology. But those contact lenses, they would put them in and they just freely rotate on the eyeball. But you need to correct astigmatism, it to be oriented the right direction. So then somebody came up with the genius idea, hey, look, we can just weight the contact so one side's a little heavier and that side will be down. And then we can correct it with contacts. Unless, of course, if they're using that method, you lie on your side for a while and the contact rotates around. And it would mess it. It'd make your astigmatism worse. Stand on your head, it'd come all the way around and you'd be fine again. So that's what astigmatism is. It is a non-uniformity in the cornea shape. Why am I going through this lecture, you're wondering? Well, I do want to try to stay as close to on schedule as I can, but it also deals with today's lab. So, since we all have our clickers, this is not the question at hand. I'm not sure what I did here. Okay, I'm going to reset this and go to the right slide because apparently, don't save. Apparently I'm on the wrong one here. Yes, I know where I ended yesterday. Okay, so here's now answer. That erases Jaren's wrong answer anyway. That he answered long before the question was ever seen. Yes, Cassie.
Should that be the cornea is too strong?
Yes. Very good observation. As you noted with the homework, we tend to just say, we treat the eye as if it's one single lens. And then we say the lens, even though only part of that is called the lens. Sally.
The lens would be curved. You can say the lens is too curved or too flat, right?
No. The lens is not material to this.
Didn't you say that myopia can be corrected by making it flat? Oh.
It's the cornea. And so Cassie was right. I should have had cornea there. Okay, we have Diksha, Helena. Okay, Helena just answered. Diksha and Sally. Okay, everybody's answered. Good. If everybody answers, then I can feel comfortable. No, nobody doesn't have it. There's not a problem there. So we had 16 and 2. Which side of vision can be described as either the eyeball too long or the lens too strong? That was the one that we started with on how we can correct it with laser. The myopia, the eyeball is too long, so the light comes to a focus inside the eyeball instead of at the retina. Or the cornea is too powerful, it has too short of a focal length. So the correct answer, most people got it. Okay, color vision. Is anyone here colorblind? Wow, some excitement about that. Austin, first things first. Statistically, we would have expected approximately one male person in this class to be colorblind. Austin made our statistics perfect. Why 1? Because it's somewhere in the ballpark of, I think, 1 in 8 males suffers from some form of colorblindness. Why male? Because it's a, sex-linked phenomenon. And you have to have homozygous problems to be colorblind as a female. As a male, heterozygous works. So, what do you mind talking about your colorblindness?
I don't care.
Okay, so what is your vision difficulty?
I think it's red and green colorblindness. That's what they call it. But there's
Okay, there are multiple kinds of red-green colorblindness.
Yeah, no.
So,
Sure.
and I don't know the difference. I know there's 2 fundamental types. I don't know the names for them. So, the red-green. Now, this picture, one thing I don't like about this picture, it comes from our textbook. They called this one yellow. We usually call it red. Well, yes, they drew it in yellow. They drew it in yellow because they called it yellow. I think the teacher has a color problem too. Just guessing. No, okay. We have 3 types of cones. They're called cones because they're shaped like cones. They're conical in shape. And those cones are what gives us color vision. And you'll notice the red and green are very similar. In fact, the conjecture is we started with just 2 types of cones, with a blue cone and a green cone. And of course, if you're going to speak about this evolutionarily, we probably would start with 1. But that the difference between the green and the red cones is a mutation, that one slightly got shifted. These curves are showing their response. So you have these cones in your eye, And this cone here responds most strongly at 600 nanometers, which is why our textbook called it yellow. It responds most strongly at all colors to the right, or to the longer wavelength side of red, or excuse me, of green. Since that's the red side of the spectrum, that's why we usually call it the red cone, because it's the one that responds the most strongly to red light. So the red, yellow, you can see there's fundamentally two ways of looking at it to decide what you're going to call it. But that cone will respond to a range of colors. You can see that that red cone will respond from somewhere around 450 nanometers out to somewhere around 750 nanometers. That's pretty close to the entire range of colors that we can see. But its strength of response is much stronger in yellow than anywhere else. And it's going to be, if you're in red, it's going to be basically the only thing that responds to red, which once again is why we call it the red cone usually. The green one has the strongest response in green, and the blue one has its strongest response in blue. And so we have our color vision, the photopic vision, with three cones: the red cone, the green cone, and the blue cone, as I put there in the correct colors. Because we have those three types of cones, we have only three colors that we really need to describe all colors we see. All of our color vision is done by computers following what we do. If you want to choose a color on a computer, your computer is an RGB. That's what the monitor is. What does RGB stand for? Red, green, and blue. And you choose an amount between 0 and 255 of red, an amount that's between 0 and 255 of green, an amount between 0 and 255 of blue. And those are going to give us different brightnesses for the different colors. Our eye is going to then measure, okay, I got this much response from red, this much response from green, this much response from blue. And it puts those three responses together and says, it's this color. So our color vision comes from how much of those three colors we see. So you can change the color of something, by making different amounts respond. Now, I know you guys aren't all from California. I love the Exploratorium in San Francisco. We went there when I was a kid on field trips. One of the cool things they have is a demonstration where you look at two blocks, and they look like exactly the same color of gunky yellowish brown. And then you take and you put a blue filter over them, and one of them looks the same, and the other one looks completely different. How can that be possible? Yeah, because your brain determines the color by just how much activation you had of each type of cone. And so one of them, they chose a single color that was in the middle of the spectrum. The other one, they took different colors at different points in the spectrum and combined them. And as long as both of them get the same amount of activation of the red, the same amount of activation of the blue, and the same amount of activation of the green, you see them as the same color. But then when you put the blue filter on, it cut out all the blue light. One of them had no blue, so it looked the same. One had blue, and it looked different. So our color vision is just the mixture of those three colors. This photopic vision or color vision occurs when you have reasonably strong light. I mentioned this in class yesterday. Weak light, the cones just aren't sensitive enough and you don't have color vision. Now we have another clicker question. What are the three primary colors of light? Okay. 2, 0, 14, 1. Now I asked this after I talked about it. Okay, I never did finish up with with Austin. They're giving him grief now, so that reminded me. With Austin's problem with the red-green color blindness, what he has is one of those two colors of cones, one of those two types of cones, either the red or the green. There's just not as many of them as there normally would be. And so he has a hard time differentiating those two colors because he's basically only getting a signal from one out of the two. And so that means the number of colors he can see is about 100 squared, or 10,000 colors. The number of colors you and I, everyone else, can see is probably on the order of 100 cubed because we have the three different colors. It's theorized, based on research, that we can really distinguish about 100 different variations. So we have about 1 million colors in our gamut. There are some people called tetrachromats. What would a tetrachromat mean? They have 4 types of cones instead of 3. And with that 4th cone, then they have 100 to the 4th power, so they can see about 100 million different colors. And so that would be kind of cool. Just as always, it's not in men that we have this good thing, it's in women. And there are people who are doing research. So we got a clear question. They're doing research on people that they think might be tetrachromats to try to typify their vision. Then when they die, they'll figure it out. Because how do you determine if a person's a tetrachromat? You have to take the eyeball apart. And of course, we don't want to do that on a living person because it kind of ruins the whole living experience. So our 3 primary colors of light are red, green, and blue because we have those different cones. And for Austin, it's going to be blue and either red or green. He'll only have 2 primary colors of light. Now, if you bring it up close to your eye, can you tell the difference?
Yes, I would say yes, probably. We're talking about if there was 2 colors that looked similar. I brought it close.
Yeah.
Yeah.
My high school biology teacher had red-green color blindness. He got a job picking strawberries. This is when he was a kid before he knew he had a problem. And he picked these strawberries. He's like, man, these strawberries are everywhere. Pick. He brings them up and he gets chasing for picking all these green strawberries. Oh, what beautiful red strawberries. Brings them right. Oh. And that's when he realized he had a problem. Because he still could see the difference if you brought it really close. Because you get enough light in there and he had a little bit. Yes?
Okay, so some people can see different colors than other people because the Akamba tribe, they studied how they see brown is black or a million shades of blue or something. So is it possible that because the surroundings you're in, you see different colors by what it develops over time, or do you think it's genetic? Or
No, it is the first thing you said. They've done a lot of research in this area. Okay. And if you name colors, you start to distinguish them better. And so different cultures will have a whole bunch of names for things that we all consider the same color. And they can distinguish the colors better because they're used to identifying them. And my culture, it's Roy G. Biv, right? That's what I was raised with, and that's pretty much what I identify. I've learned to say cyan. I know that there is a thing called chartreuse, but I couldn't tell you even anything what it's like, right? But basically, yeah, if you learn to identify it, then you can perceive it easier. But then the people who are tetrachromats, they can see variations that we can't. So 2 colors that would look exactly the same to us, to them might look significantly different.
So you can train yourself.
Well, you can never train yourself to see what that tetrachromat sees.
Yeah, not them. But the other.
But yeah, you can train yourself to perceive colors better.
Okay.
And of course, that's not really physics in that aspect, but it's tangential rays. Somebody else had their hand up. Right.
That 4th cone, do we know what its primary color is? Or do we
I didn't look it up this year, so I can't remember what the research is on the 4th. Yeah, just look tetrachromat. You'll find plenty of info. Okay, reflectivity and color. I started out the very first mention of optics before exam 2, talking about how we see color in people's clothing. I think I used Lindsay's shirt as an example of a color there. if we look at Chad's shirt, we probably all agree it's white stripes on a blue field. How do we see that? Because light is being reflected. It's pigments that are absorbing light that give it its color. So we talked about the three primary colors of light, red, green, and blue. Well, for Chad's shirt, we use pigments to absorb, and the pigments we use are going to be pigments that absorb one of the primary colors. So for instance, I might have a pigment that just absorbs red, reflects the other colors. In physics, we break the colors down. We just say red, green, and blue, okay? So I have red, green, and blue light, and I might have a pigment that the light hits Chad's shirt and it absorbs, I said red, absorbs red and reflects blue and green. What is our eye going to see with blue and green? We call that color the complement of red. And so if we have blue and green mixed together, our brain takes those two colors and says, blue plus green is equal to cyan. And so cyan is what we call a primary pigment. Because if I put cyan in his shirt, it'll absorb blue, but the green, or excuse me, absorb red, but the green and the blue will be reflected black. So that's one of our primary pigments. Then I can make a pigment that's going to absorb blue. So it would reflect red and green. And if it reflects red and green, our eye sees yellow. So yellow is a primary pigment. And finally, I could absorb green, so I would reflect blue and red. And blue and red together is magenta or purple. So those colors there, cyan, yellow, and magenta, those are your three primary pigments. If you are an artist, you should be able to make any color by mixing the right amounts of cyan, yellow, magenta, as well as lightning agents of some sort. And so those would be the pigments you use. Now, it wasn't until I became a physics teacher that I realized that art people saw different colors or used names that were different for these kinds of things. You'd think I would have figured it out when I was in college and had art majors as a roommate, but no. So, how many people have taken a painting class where you talked about the primary pigments? Okay, got at least 4 there. And what did they say were the primary pigments? What? Not white.
I don't remember.
Well, oftentimes they give you a set of colors that doesn't match this. And the reason it doesn't match this is historical in nature. Using just natural products, it was historically very hard to find good substitute or good cyan or magenta. And so they said, well, let's just, instead of cyan, let's use a blue pigment, a pigment that is going to reflect blue. And instead of magenta, let's use one that's red. And the yellow they could find, so that stayed yellow. I think those are what they use. Now, I could be wrong because I never learned these. It's just from students saying, no, I learned this. They went with these substitutes because it was easy to find pigments. Now, with those substitutes, you can't get the full color gamut, so you're going to limit a few of the colors you can make. But it's a pretty good approximation. You get a pretty full gamut. These days, you can find nice, cheap pigments of cyan, yellow, and magenta. And if you use just those, you should be able to mix together and get all of your other colors. This being said, printers How many people have had to purchase color ink for their printer? And what does it have for the colors of the color ink? It has C, Y, M, and K. Now, I was corrected last year. K does not actually stand for black. It stands for something else. But it is black. That's because when you're putting ink on the paper, you're putting pigments down. And so you're using your primary pigments, cyan, yellow, magenta. And then the black is to absorb all light. I don't have it queued up, and so, well, see if I can. Yeah, I'll play this video.
Inside these laboratories lies a dark secret. Something so dark it transforms any surface it touches into an apparent abyss. This is just an ordinary piece of scrumpled up tin foil with all the lumps and the bumps that you expect. Until that is, I turn it round and they disappear. It's like staring into a black hole. This is Vanta Black, the blackest black ever created. It seems to remove all the features of the surface it's on. Let me show you just how black it is. I've gathered together a collection of black objects. Crucially also, my super black material here. The thing is, if I shine a beam of light onto each of them, some of the light is reflected back to me. Until that is, I go on my super black material, the beam of light disappears. The reason why it's so black is because it absorbs virtually all light, 99.965% to be precise. This achievement is the work of British technology company Surrey Nanosystems. Ben Jensen is their chief technologist. So Ben, why create something so very black?
We were tasked originally with making a material that had about a 1% reflectance, and that was for use in satellite imaging systems. When it's inside the telescope, it actually absorbs the stray light that comes in, so more of the target light from the star hits the detector and you get a clearer signal.
The secret to the substance's amazing light-absorbing properties is the material it's made from. Microscopic carbon nanotubes, just 1 atom thick. Imagine that these black straws are carbon nanotubes. And when a particle of light comes in, rather than bouncing off the surface, it ricochets down between the nanotubes until it's absorbed. But how do you paint something with carbon nanotubes? Ben is going to show me by coating something more complex than they have ever done before. A bronze mask of my face. We're going to plunge it into darkness.
You know what? This is a real first for us. It's an incredibly complicated shape, so we're not really sure how it's going to come out.
First, a black layer of carbon nanotubes is carefully sprayed onto the mask's surface.
Well, it's very black. That's typically the performance that you get from the paint that they use inside the Hubble Space Telescope. So, good, but not exceptional.
To make it exceptional, the mask is placed inside a plasma reactor. This breaks down some of the bonds between the nanotubes, allowing light particles to enter and be absorbed. 10 minutes later, and the super black coating is complete.
That is very strange indeed. You can't actually see any of the details because you can't see my moustache or the beard or my eyes just not there.
No, I love it. I think that's come out really well. Really, really well.
Looking at the mask from the side, I can make out my profile and the outline of my face. But as it turns round, it completely disappears. It's only when you look at the ordinary black finish that you realise just how black it really is.
I'm really impressed with this stuff. This is more than just some sort of clever, techie optical illusion. This stuff has enormous practical application, and it could revolutionise the way that we see the universe.
Wow, it's totally mind-boggling, that. Yeah, and if you would like to see for yourself if you can't see anything, Marty's Vanta black mask will be on.
Okay. Now, what is black? Black is the absence of light. And so you look at this tabletop, now we all would probably agree this tabletop is black, but we can see light reflected from it. So it's not a perfect black. That Vanta black is very, very absorbing, very little gets reflected, and they explain why. And so you get a much better black. You can't see black because it means there's no light coming from it to see. A controversy regarding Vanta black. While industry technology can use Vanta black across the board, they have licensed that only one artist can use Vanta black in artwork. And so all the other artists are like, wait, what about us? We want to make good artwork and we'd like to have a deeper black. And no. And since it is the company's product, it's not like the product belongs to humanity. The light does, I suppose, but it causes some problems. It's in our community. So this slide here, which is maybe my next to last slide, is just illustrating how we get the colors. For instance, Chad's blue shirt. His blue shirt is going to reflect the color blue. What about the color red? It's going to absorb it. What about the color green? Absorb it. Now that's a light blue. Because it's light blue, it's going to reflect some red and some green to go along with the blue and lighten it up. If it was perfect blue, it would be only reflecting blue. So it's not just blue because it's a light blue. And in fact, pastels, you're just putting in something that reflects across the board to lighten things up. That's what a pastel means. So this picture here of the black object absorbing all the light, that's why I thought I should show you the Vanta black. A white object reflects all of the light that hits it. If the only light that hits it is red, it'll reflect red and look red. So if you have a white shirt such as Reagan's wearing, if he goes into a room that has a red light, it's going to look like a red shirt. If you had Toussaint and Reagan in the same room with that red light, their shirts would look the same color. Because Toussaint's shirt is reflecting red, Reagan's shirt is reflecting all colors. If you only have red light, they're going to reflect the same thing. Okay, so what are we doing in lab today? I got 2 more slides here. This one here is about light sources. You also probably remember that I mentioned the clothes I was wearing the first day I talked about colors. They looked like completely different colors in my closet, and then when I got out in the light, they looked like the same color. Because I had different kinds of light sources in my closet than what the sunlight puts out. And so there's different colors to be reflected, and that makes a difference on my perception. So if you're out there shopping for just the right color dress, because quite honestly, virtually nobody's looking for just the right color shirt. If you're looking for just the right color dress, you really want to make sure you see what that dress looks like in the lighting where you are going to be wearing it. So if you're going to be wearing it outdoors, take it outdoors to see what it's going to look like, because the colors will be different than they will be inside the store. It's not the store's fault. It's because the store has something like maybe fluorescent bulbs. You see the fluorescent bulbs have that green emission spectrum. Those are the colors you're getting. Primarily, you have a blue here, and then a green here, and then a red here. And so the fluorescent bulbs are giving you just those 3 colors, which we perceive as white. But you have something that absorbs in between. It's going to look different if you have that compared to, you can see the incandescent bulb is the bluish line. The sun is the orangish line, very different from this. Yeah.
This may be completely unrelated, but so what was going on with everyone's eyes when that dress came up online?
That's a good question. One of my former students was just, well, I'll admit this to everyone publicly. There's a little thing you can do on the internet that tells you the age of your eyes. And it has you do things, and that's one of them. And you know, like what color you see here, what stands out here. It said I have 87-year-old eyes. That made me angry right there. And she said, well, you know, that blue and white dress, it has to do with the relative number of rods versus cones. I haven't looked into it carefully to know exactly. But it definitely does have to do with rods and cones. I believe her on that front. And yeah, it's really annoying because it's very clear that that's a primarily white dress with gold banding, right? Very clear. No, it's one of those odd situations where there's not really a correct and an incorrect. Okay. Thank you for bringing that one up. The last thing I want to bring out, I also had a friend on Facebook post about this just yesterday. Our eyes are pretty amazing. That top picture is just showing different graduations of dark to light. But our brain does not read it as simple graduations. The middle graph shows you what the actual, we call optical density, how much light it's absorbing, how much it's reflecting is. But our brain identifies the edges. And so it adjusts the sensitivity. And the honest truth is nobody knows exactly what the process is. But we do know that our brain accentuates the change. And that's why you've seen that thing that shows like a suitcase that's flipped open and the top side looks one gray and the bottom side looks another gray. They're exactly the same colors of gray. It's just the backgrounds and the variation in the center that makes your brain think they're different. It's because our brain does some pretty amazing processing, which allows us to have some really cool optical illusions we can make because of the way our brain works. We have simple things like persistence of vision. If you look at something for a long time, your brain will kind of reduce its sensitivity to what's there because it's going to look for the changes. And so you look at something for a long time, like you look 30 seconds at this picture that's a black and white cutout, and then you look away at just a white background, and suddenly you're going to see where the black will stand out as a different color, and you'll see a reverse image. Right? You guys have probably seen that, like you look at this thing and then you look away, you see the face of Christ. Like anyone knows what the face of Christ looks like, that's beside the point. You see an unknown face. And that's because of the way our eyes and brain work. And of course, yeah, nobody knows the ins and outs of it, except for I believe God does. Okay, why did I go over all this? What are we doing for lab? You probably have read by now that there is no specific procedure. You just need to have something that is a hypothesis and test about the things we've talked about, how the eye works and how we see things. So you could do something that deals with hyperopia or presbyopia or myopia or astigmatism or color vision, and you need to be able to test it with our equipment. So what's the equipment? I have a set of cylindrical lenses and mirrors. There's is it converging or diverging? Okay, well, go with that. Is it convex or concave? Convex. It's convex because it's thicker in the center. And if it's convex, is that going to be converging or diverging? Converging. That's right. So this is convex or converging. And then I have this here. It's concave. Diverging. Now these are cylindrical lenses. They're not spherical, so you can only focus in one direction. Not a big deal, you just have to realize I'm only focusing in one direction. This also has a mirror that is planar on one side, concave on one side, and convex on one side. Also has a little tank you can use. You can pour water in there and make lenses that are a plano concave, a plano convex, well, two plano convexes. So you can make water lenses if you want. So that's one thing you can use. With that, we have light sources that will put out parallel rays of light, or you can choose colored light, depending on how you have it set up. Or we have these setups here, which have a lot more things, a lot more things. This here is a holder to hold a lens, and then we have, well, that's a mirror there. But there are different types of lenses that you can use. So these are going to be spherical lenses rather than cylindrical lenses. Find what you want to do. Make sure you talk to me, or when she gets here, Erika, about what you want to do. We say, yeah, that's good. And that's it. There's no specific procedure. So groups of two, and we have more of this equipment if you need it.